So this talk is what happens when you do a talk on something you know absolutely nothing about. I have really been fascinated by AI, but it was a black box, right? Who knows what's going on inside it? You hear all the buzzwords, you read all the articles about all the money being spent on it. What's going on? Like, what is inside that black box? So I spent the last 2 weeks reading articles, going through the math equations, trying to decipher what actually AI was, and hopefully I've digested it down to 50 minutes, and hopefully I'm not going to lose you along the way. I tried to make it as easy to understand as possible. There's some really strong take-homes that will help you when you start reading about AI's hallucinating or traffic accidents. Now you'll be able to, in your head, go, oh, I understand what's going on. I know why this happened. As I said, I've simplified a lot of stuff. Some of it is maybe not exactly accurate, but the take-homes are valid, and I guarantee you're going to walk out of here being able to read AI, knowing more than people around you about it, and being able to draw conclusions and make judgment calls about whether you should use it yourself. So when I was a kid, I remember getting my first combination lock. I was heavily into Legos. And it's before the internet and before, I was a little kid. And I remember sitting there, like I'd hold it up to my ear and hear it and hear these little clicks. And I figured out how it worked, or how I thought it worked. And then I built myself a Lego combination lock. And lo and behold, it worked exactly the way this one worked. And it was sort of the start of my exploration about how things work. And I was fascinated with it. And this went on, and a couple years later, I took my dad's favorite German camera, and I wanted to know how the shutter worked. And unfortunately, I broke it. And he was not too happy about it, but he was good in that he didn't shame me about it, even when, a year later, I broke the family radio. So then I went on to bicycles and was working on bicycles for years, and then my grandfather taught me how to rebuild a car engine, yada, yada, yada. I went into college, and I was fascinated about living things. And halfway through college, I discovered protein structures, three-dimensional protein structures at atomic resolution. And it started a 10-year love affair with protein structures. So this is the flu virus. I worked on the coat protein right here, the blue, the teal or maroon-colored coat protein. It's called hemagglutinin. It's almost exactly like the spike protein we've been reading about with COVID. And the thing that I was so interested about was you get the flu this year, and you get antibodies to it, and 2 years later, you get the flu again. How does this happen? Well, it turns out the outside of the coat protein of this hemagglutinin has an area that doesn't do anything with the structure of the protein, but it changes the shape of it. So your antibodies that recognize the shape of the old one don't recognize the shape of the new one. And we're living through this now with COVID, right? We have a new variant every 6 to 9 months. If you look at the graphs that show the distribution of each strain, you see it starts off a little tiny bit, and then 6 months later, it's the majority. And then underneath, there's another one starting, and it grows. And I think we're all now to the point where we have antibodies that help us a lot, but I think we're still going to keep getting mild cases of COVID because that coat protein keeps changing. So AI is sort of, when I started this investigation, this is what I thought of AI. You have a question, AI does some magic blob, out comes the answer, right? This is, you may be more advanced than I was, but this is all I understood. And it took a whole bunch of NVIDIA cards, right? So at the end of this talk, you're going to understand what's in the blue box. I guarantee it. So let's start first by talking about the NVIDIA chips. The current one that we keep hearing about is the H100. It goes into a chassis which has an Intel processor in it. It consumes 700 watts when it's going flat out. From what I've been able to figure out from estimates, that 700 watts becomes 2.5 kilowatts when you include the power required for cooling it, and the power required from the server. So 2.5 kilowatts per processor. I think someone said there were 8 cards in a chassis. Someone else was talking to me today, 2 days ago, about how the 4U high rack with 8 of these cards in them, the power supply for the rack could only actually handle 2 of these boxes, even though it's only a total of 8U high rack space. So the follow-on, this, by the way, is they call it the Hopper GPU. So the next one is is what they're calling a super chip, and it's got the GPU, and then it's got an ARM core on the same sort of substrate, so you get much higher bandwidth between the two, and they're basically doubling the speed with which they can do things, even more so if you're doing what they call sparse calculations. Now, sparse calculations, most of these calculations are just floating point math. So sparse calculations are where one of the terms is 0, and they've got an optimization in this processor where they just go, oh yeah, it's 0, I don't have to do anything, I'll just return 0. So this GPU here is called the Grace Hopper GPU, and Grace Hopper is someone, I had to look this up because I knew she was really important, but I couldn't remember what she did. So she was working in the days when computers were just starting out. She was working on several different machines. She had to learn a different language for each one. She said, this is really silly. Why do I have to do this? I have a computer here. The computer should be able to translate some set of instructions to a particular processor, a particular computer. So she's the one who created compilers. Like, that is so cool. So she created COBOL, which I think is still, unfortunately, in use. So you can thank her for that. But she did, this is like amazing. This is one of those, oh my God, that's so obvious, why didn't I think of it? I'm sure there are many people who, this woman comes along, it's an age when women were not as respected as they are now, and she's a mathematician, and she goes, oh yeah, this is really obvious, this is what we should do. So let's talk a little bit about how many NVIDIA chips are being shipped. 2023 was 500,000. This year is projected to be 2 million. That has power implications, right? These things are sucking down a boatload of power. So I went to this paper, projections on power usage from 2022 to 2026. It is by, I can't remember what it's called, the International Energy Association, I think so. It's a nonprofit. It's all the member countries contribute to it, and it does research on power usage, projected power creation. It's a really easy to read and very interesting article. I highly recommend you look at it if you want to follow on more. So let's look a little bit about their projection on data usage. On electricity consumption by data centers, right? So what we see is in the US now we have just under 4% of our total, here we are. Just under 4% of total, or over 4% of total consumption as of 2022, and this is going to go up to 6% for 2026. So 6% of the total electricity usage in the US is going to be data centers. It's pretty incredible, isn't it? It gets even more incredible when you look at Denmark and Ireland, which are going to jump to in the 20s. So Ireland is supposed to be about 30. Denmark is supposed to be about 18. This is of the total electricity consumption of the entire country. So if we look actually at United States, for instance, the actual total energy consumption isn't going to go up very much in those 4 years, but the data consumption for data centers is going to be pretty dramatic. So if you look at global data center consumption, we see that it's basically going to double in this amount of time. It will end up being, at 2026, the same as the entire consumption of Japan or the same as a quarter of the entire consumption of the United States. I'm not sure that these estimates take into account the fact that the GH200 is consuming almost 3 times as much power as the current chip, right? It's a 2 kilowatt consumption just for that card. The H100 is 700 watts. So I wouldn't mind betting this is an underestimate. And I think what's going to happen is governmental regulations are going to have to start putting some sort of dampening on the consumption. In the news over the last like 3 or 4 weeks, Microsoft has said that they plan to, or is under contract to, restart the 3 Mile Island nuclear reactor. That's just under a gigawatt. So there's some, I think that's going to take about 3 or 4 years to happen, but it's really interesting that a nuclear reactor that's on the same site as one that melted down, that had been decommissioned, I think in 2019, they're going to turn it back on. They're going to incur that incredible expense of refurbing the turbines, refurbing the steam generators, going through an entire round of recertification with the Atomic Energy Commission. It's a really expensive process, but they think it's worth it. And even more alarming to me was OpenAI said that they were proposing that over the next 4 years or 5 years, they wanted to open 7 data centers in the US. And each of these is going to consume 5 gigawatts. So 5 nuclear power reactors of electricity. That would equal, if you do the math, that turns out to be roughly, just those 7 data centers would be 10% of the total US consumption. So if this goes forward, there's going to be a squeeze on power globally, and people who are heating their houses, cooking their food, paying their electric bills, as we saw with the whole Enron scandal in Southern California, whenever it was, there's going to be squeeze and people are going to all of a sudden have these huge electric bills. And I'm hoping that the governments step in and add a little dampening there so people don't get hit with this huge expense. So we can do a little back of the envelope calculation. I always like to do this when I read numbers from reports. Does it make sense? That's what I always ask myself. Does it make sense? So here I have the total number of NVIDIA H100s that are projected to be shipped this year, the hours per year, and the watts per chip. Now this is the 2.5 kilowatts. So I think that's pretty accurate for how much power is required for the data center for that 700-watt chip. And I come up with a total of 43.8 terawatt hours times 3 or 4 because we're going from 20 to, we're sort of doing an average, or actually times 3, we're doing 3 more years. So this is a minimum for 2024, 2025, 2026. So that would be 120, 130 terawatt hours. That would be roughly a third of the growth that's projected for global data centers just from this one chip. I think so I'm in the ballpark. The numbers are in the ballpark. So let's start talking about AI. I've broken the talk down into 3 sections. Learning about AI, Q-learning, which is sort of machine learning without neural networks. It's been around for a long time. One of the equations, I think, is from 1954. And there's a reason that machine learning didn't really take off until recently, and that is the capabilities of the hardware really weren't there. So let's first start talking about types of learning, because this is important when you start reading about AI and AI training. There are 4 different ways that AIs learn, and the end result data is different for each one. So the first one is supervised. Supervised is where you have an expert, you're showing the AI stuff, and the expert is saying, this is this, this is this. So imagine you're training an AI to recognize, certain type of tumor. So you got the doctor there, and the x-rays are coming through, and he goes, yes, tumor, no tumor, yes, tumor. And the AI is just reading and ingesting all these images and then scoring them yes or no, yes or no, yes or no, yes or no. Or say it's like recognizing different types of butterflies. So you have one butterfly and another, and every time a butterfly picture comes up, the expert goes, yes, this is it. This is this type of butterfly, this is this type of butterfly. And you train this model, you train this AI so that in the end you can show it a butterfly and it knows which one it is. I think that's going to be the way that AI is used in the medical field. Unsupervised is, I'm just going to feed you data, and you can figure it out and classify it however you want. And then when I give you a test case, you can give me a recommendation. Think of Netflix. For those of you who have Netflix subscriptions, I see very different movies on my page than my wife does. She sees all the historical dramas that put me to sleep, ones from like England in the 18th century and the people in big dresses, and I see all the ones about spies in the Cold War, And so if she logs in and she hits Tim, she's going to get Tinker Tailor Soldier Spy, and if I log in as her, I'm going to see Downton Abbey or something like that. So, it's trained on what we're doing, and then you hit the little like button, and then all of a sudden, like I did that for a Spanish drama, and all of a sudden I've got a whole bunch of Spanish dramas. So it's training itself on me. There's nobody telling it what's right or what's wrong. It's just looking for patterns. Reinforcement learning is goal-oriented learning. We've got some problem, and we want it solved. And we can scorecard it and say, yes, it's solved, no, it's not solved. Playing a game, for instance, or finding a solution for how to cool a data center. This is the only type of learning I'm going to address today. The other ones are similar, but there's so much to cover. I had to narrow it down so I could give you a really good understanding of how one type of AI works, and this is the one I chose. Diffusion AI, machine learning, is what's used apparently for, it's the revolution that happened that allowed training for visual images to happen faster. I will totally admit, I understand sort of a little bit about how it works, but I couldn't give you the deep dive that I'm going to give you on reinforcement learning. So the top equation is the Bellman equation. It's there. I want to say you won't see another equation today, but there is one more, but it's really simple. I don't want you to have to think of this, right? This is what I've spent the last 2 weeks looking at. The bottom is what we're going to deal with. There's a little agent here. There's a banana, which is the prize, and we're going to march forward that. And because I think it's much easier, at least for me, I'm not a mathematician, it's much easier for me to think conceptually in terms of like models and really simple math rather than thinking in terms of equations. My daughter is a really good mathematician. She could look at the top one and go, oh yeah, that makes sense. And I have to sit there and it takes me like 10 minutes to get through that one. So, and a lot of help. I couldn't do it by myself. These are the terms we're going to cover today. I'm showing you this because you may know these. I certainly didn't when I started this. But at the end of this talk, you're going to be able to use all of these terms in a conversation and understand what they mean, or hear someone talk about them and understand what they mean. So this is our target. Okay, this is where we're going to go. Next up, I want to show you this. So this is a couple robots programmed by DeepMind. They are playing soccer, what we call soccer, we call football. And it's really cool, isn't it? This is where I want you to understand where we're going, okay? This is something that we could do programmatically. If I'm like a programmatical engineer, I do object-oriented coding. The AI is completely foreign to me in terms of implementation. As I said 2 weeks ago, it was a black box. So I would, if it was up to me and I was going to, given a team of people and said, create a program that will run soccer for 2 players on the side, I would start by creating a subprogram that allowed the robot to roll onto its back. Then I'd get one that allowed to sit up. Then I'd come with ones that allowed to stand up, take one step, turn right, turn left, stop the ball, and kick, right? And there would be a lot of work in this. Like, you know, the robot was slightly off balance, et cetera, et cetera. You'd have to accommodate a lot of things. Then you'd have to do a whole bunch of other subroutines that would get you state information. What state was the robot in at this particular moment in time? Where was the opponent? How fast and what direction was the opponent traveling in? Where was the ball? Where's the goal? Where's the robot that you're controlling? And then you'd have to set up this sort of controlling routine that would be a loop, and it would first get the state, determine a strategy, like I'm not going to kick directly to my opponent, I'm going to kick to the other guy so he can kick in, take an action, loop, okay? Maybe a team of 20 people for 3 years, I don't know. A lot, right? It would be a really complicated problem. The good news is you could probably run it on a M1 Mac Mini without any problem and run all day long, and it would use whatever the Mac Minis are using now, 49 watts. But it's a human-intensive process. So instead, artificial learning includes a lot of trial and error. This little guy here is trying to figure out how to stand up. Okay, and it's just trying things. No, that didn't work. Okay, let's try something else. No, that didn't work. Let's try something else over and over and over again. Sometimes these trials are done where it's a simulation of the physical object so they can do it faster. But it's basically just trial and error. Okay, so this is one of the key things about AI. We're doing a boatload of trials, and a lot of them are going to fail. I thought this was really interesting because in 2016, DeepMind, Google's AI, beat the #1 Go champion in the world at Go. And it's sort of a pivotal moment. According to what I've read, Go is like considered more complicated than chess. And I thought, oh my God, this is really cool. So, and this was done with reinforcement learning. It wasn't done with supervised learning. The AI wasn't trained by watching a whole bunch of other people's, of players' Go games. It was trained by trying things over and over again. And the key thing here was that the AI played moves that nobody had ever seen before. Okay, so AI, I think, is really good at finding novel solutions because it's just doing trial and error. Now, the problem with doing trial and error is you're going to fail a whole bunch of times, and you're using a boatload of electricity, just like truckloads. So I think that's interesting. So let's go. We're going to do this in 3 steps to get you to the point where you understand AI. And we're going to start with what's called learning by value. So here I have my little robot guy. He's starting out in a grid. There's a value which is sort of like, what's my prize? He can only see the squares next to him. And the prize is the banana, which is a 1.0. And he's going to move around at random until he gets next to the banana. And then he knows that when he moves into where the banana is, he can go back and reset the value of the square he was in before. And we could say the value of the square before is the same as the price square, but that wouldn't make any sense because very soon they'd all be 1s, and he wouldn't know which way to go, right? He's trying to go to a greater value. So instead what we do is we say there's a scale factor we apply when he goes forward from a square with 0 to a square with a value. We just multiply, in this case, 0.9 by the scale factor. So if this guy does, by chance, in his random walks, he's doing random when he can't figure out what to do. If by chance he goes around this way, we're going to see he's going to get 0.81, and then very soon he's going to end up with this. Okay, so this is learned by value. He's got a map, he can find the solution, but notice something. If he starts off down here, he can make it in 2 moves, but he doesn't know that. So he's always going to take the long trip around. Every time he gets anywhere around here, he's going to end up taking the long way around. okay? This is the problem with learn by value. So instead what we do is we look at learning by quality of action. How good is the action I'm going to take? And it's called a Q-value. It's represented as a number between 0 and 1. And all of the possible Q-values for a given state, all the possible actions, the Q-values, all add up to 1. So it's a probability. And we use it later as a probability. So when the guy is sitting right here and he has to choose which way to go, he sort of takes a random guess, but it's weighted by this probability. Probability, so that he knows that he could go like a quarter time he's going to go up, a quarter time he's going to go to the right, left, and down. This is important because it gives us the ability to keep trying things that we may think aren't going to work. Okay, so even when this guy is totally trained up, he gets here, he's still doing, he's doing this initial state, so he doesn't know that he hasn't had this experience yet. He goes over to here, and then he changes his Q values, his probabilities, because he now knows that it's better to go right than up or left or down. Right? Notice that we didn't instantly peg it on one end or the other. If we instantly said, oh yeah, it's going to be like 100%, 1.0 to the right and 0 to the other two, we close off the ability to try and look for other actions, other ways of solving our problem. So we're going to, train our model, if you will. We're going to modify our Q values, and then eventually we're going to end up in this situation where the Q values for this square here are heavily weighted towards going up or to the right, because those both get us within one step of the solution, and heavily not weighted towards going to the left or down. Notice these aren't 0, because we still want to try them every once in a while. There might be some solution that we didn't know about. That happens only once, some convoluted way of solving that actually is an improvement. But we want to most of the time do what we now think is the right thing. So this is Alan's 6 seconds. Thank you, Alan. It's a great way to solve stress. This is from a watch store here in Gothenburg. And if you're like me, you lived with an Apple Watch for a couple years, and then you thought, oh, wait a minute, I don't really want to be bugged all the time, so I went back to an analog watch. And I'm sort of fascinated by older analog watches. In this store here in Gothenburg, it's about 30 minutes away from here. He has a fabulous selection. It's Christopher. It's a fabulous selection of vintage watches. He also has a presence on the web if you want to go and order one and have him ship it to you. He's a really nice guy. If you want something to do this afternoon, I highly recommend heading over to his store. He's got more vintage watches than I can imagine. They all seem to be in really good shape. If you want to buy something on your way home for your partner or a friend or yourself, these two women run a fabulous silver workshop like 5 minutes down the road from here. And I've bought several things from them. It's very much the Scandinavian design of silver and stones. I think their stuff is really beautiful. So I highly recommend, if you want a little break, you head down there. Okay, enough of the distraction. Let's go back to Q-learning. Q-learning is what we call working on what we've described, working and finding or optimizing the quality of actions. Since we're going to use computers, we have to have a way of describing the squares in the setup, so we're going to call it the state. The state is going to be an x and y value, and once we do all our math and we've trained our model, we'll end up with something like this. Now, each of these squares has the same number. I'm sorry I didn't have time to go and change them. They should all be different, but we have for each square, for each state, we have the Q1, Q2, Q3, and Q4. And we can think of it like x and y goes in, and we have a table, and we look it up, and our Q values come out, okay? So this looks, you understand what's going on here, right? So what we're going to do now is we're going to take the center part out, and we're going to change it. And we're going to put an artificial neural network in there. And this is where the magic starts happening. So this is called deep Q learning, or DQN is the way it's abbreviated. You'll see it if you start reading. Artificial neural networks are made of neurons. Neurons are just simply an accumulator which multiplies together all the inputs and outputs the output to another set of, the same output to all its following neurons. So this guy's getting input from all of these guys, and he outputs to all these guys. And the connections are called synapses. The one magic thing about this is that it's not always the same number that goes through to each of the guys. It's a weight. We have a different weight on each of these synapses, and the only thing that changes when you train an artificial intelligence model, a neural network, the only thing that changes is the weight. That's it. All you're doing is you're changing weights. So you have all these guys connected up, and you have your inputs, you have what's called your input layer, which is where we're going to get everyone in. You have hidden layers, which don't have any external connection, and you have your output layers. And they're all connected via, they're all connected via synapses. The purple things are synapses. And each of these synapses, they all have the same, they all have the same arrows, but they all have different weights. And their weights are unique, and they get changed as we train the model. And so as the model gets changed, as we go through all our random motions, we're going to change those weights. And at the end, if you ask someone to explain why it is that the AI model works, they can't explain it because it's just this set of weights that you've asked, you read the things about ChatGPT or other AI models, how do they work? Well, we don't really know how they work, but it's a set of weights, and we set up this whole machine, and we let it run and train itself, and then we end up with all it is the hardware and a set of weights. So to solve our problem, we put in our x and y for our little guy looking for the banana. His current state, say 2, 0 or something, it goes into the hidden layer. Now, if it just started out with each of these weights initially being the same thing, each of these hidden layer neurons are getting the same inputs from x and y, they'd all calculate the same number. That would be totally useless. So what happens, the other piece of magic here, is that all of these weights initially are randomly set. So every time you start an AI training on the same data set, you're going to get a different answer, but you're hopefully going to converge on the same answer eventually. So that means because they're all have random weights, each of these hidden layers are going to calculate some different value, and then they're going to pass it off to the output layer, and the output layer also, all these neurons have different weights, and so the output Q1 through Q3 they're going to be unique numbers. They're not all going to be the same numbers. So, and then the output is going to go to our Q values. Wait a minute. These are, we're starting with, in our case, numbers 0 through 4 or 0 through 2. And we're going to end up multiplying by something and multiplying by something. Q1 through Q3 is not, they're not going to be numbers. They're not going to add up to 1. They're not going to be probabilities. So we have to have what's called a softmax function. It just takes all our numbers in and sets them so that they're in the range, so that their sum is 1, exactly 1, and they're just basically, it's a scaling factor. So here's our guy. Here's his initial Q values. And we then figure out what's called a loss, which is basically how far off is our model. And in this case, how far off, we're obviously way off, right? Because he thinks he should go right only 16% of the time, but it's the right answer. So this is the only equation I have here. You can't really figure out the difference between what he should do and what his Q value is by just doing subtraction, because then you'd end up with some negative values and some positive values. So instead, we do the square of the difference, and that ensures that it's always that each of these terms is going to be positive, and we're going to, even if one's even if the target value is less or greater than the Q value we calculate, the square is going to be the same amount, so we're going to add the same correction factor. So this loss value goes back into our, we compute it, and it goes, this is called back propagation, which you also probably will hear about when you start reading, and it goes back to our weights. Now, if you think about it, in the case where you have maybe, well, in this case, we have 30 neurons, right? So if we were going to do something like, 30 synapses. If we were going to do something like find the global minimum for this, we could take each of these weights, and we want to apply a loss factor or calculate a loss factor. We could sit there and come up with like 1,000 different values for the weights, and then compute the loss factor for all for the 1,000 different weights for each synapse. But then we're looking at 1,000 to the 30th power calculations. Man, that's going to take forever. So we need a different solution, right? And the different solution is, once we get a loss factor here, we take each of these neurons and we change their weight just a little tiny bit. And then we see, did the loss go down or go up? And if it goes down, we know we're headed towards a better solution. So we can say, okay, the loss, the weight for that particular neuron needs to go down. We choose some random amount that we're going to send it down, and we send it down that amount. And then we iteratively do that with all 30 synapses, and we come up with a better set of weights. And we redo the calculation again. We go back and take our input, and we use our new weights, and we go through the hidden layer and come out with a new loss factor. And this is our iterative process. But we're not iterating with the same input each time, right? We're iterating with a different input each time. And this is how we're training it. We're training it by not using a static set of information. Like if you're training an AI on pictures of dogs, you do this once with a picture of one dog, and then you do it with next picture with another dog. It's not like you're training it on one picture, because then you're going to end up with an AI that recognizes one picture of one dog, and you show it say it's a black lab, and all of a sudden you've got a poodle, and it wouldn't know what to do. So by using a different state, a different first step each time, we're going to end up training the AI for a much more general problem. So let's go back to our Go situation, right? Go is a game. I've never played it, but I'm now really fascinated about it. It's 19 positions on each side. It's got black and white tiles. You are trying to either surround your opponent so you can capture him, or mark off part of the board. And once you've marked off, the person who's marked off most of the boards and it's captured the most of the opponent's pieces is the winner. So this, if you think about it, lends ourselves exactly to the AI we just went through with the guy trying to get the robot trying to get the banana, right? So we have now 3 states, or 3 values for each state, and each state is just one position on our board. And the 3 input states, or 3 values, are no tile, black tile, or white tile. And we have then a set of hidden neurons, which these are all interconnected, so you can imagine how many thousands of connections there are. We have our output neurons, which are going to be, after they go through the softmax, becomes the probability that we should, or the quality of the action. And what is the action? The action is whether we should place a tile on that position, right? So there are 360 positions. The probability of placing a tile in any one position has to add up to 1. And we're going to come up with a probability for each position, and then we're going to go and run the AI and use that probability as a way of determining whether or not we should put a tile in that position. And we're just going to run this a gazillion times, right? So remember that this is the only input information is this next position closer to winning the game? Right? There's no strategy input here. It's just trial and error. It's just a boatload of trial and error. And this is why it took so long for them to train AlphaGo to play Go. But this is also why it came up with a solution that nobody had ever seen before. Because it was trying things that people, if you learn to play Go, you'd like watch people. In the old days, you watch people play. Like I like to play backgammon. I watch people playing backgammon at the square in Mill Valley, and I learn things, and I sort of work things out in my head, and then I play a much better player and get totally decimated, and hopefully you learn from them, right? So it's the same with Go. Go has been passed down for, 2,500 years, and people have been watching people play Go for generations, and those cool moves get passed along. And here comes this AI, and it just blows it all out of the water because it tries all these things nobody had thought of before. And it did it only by trying a boatload of things that didn't work and coming up with something that did. So hopefully you now know what all these terms mean, I hope. If not, ask me afterwards. And the key takeaways are that AI is using random, first of all, that it starts off with a random set of weights, that you can only change, the only programming you're doing is changing the weights, right? And that it's trying over and over and over again all these possible solutions, most of which won't work. So this is why we're using so much electricity. It's doing, billions of calculations to come up with a solution. So let's talk a little bit also about ways that AI is failing and why it's failing. I live in San Francisco. I drive around, and there are all these self-driving cars. And it's a common joke in San Francisco that the cars eventually or occasionally get to a point and they just stop in the middle of the street, and they just sit there for like a minute and they drive on. But what's a sort of a hidden secret is when they stop, they're reaching a point where the AI doesn't know what to do. And there's actually a room filled with people in front of computers who get a little ping when the car stops, and then they have, they pull up the video, they pull up the thing, and they map actually where the car should go. Say there's a construction zone and somebody's sitting there with a flag, and the AI doesn't know what to do with the flag. He's never seen the flag before. He's only seen a guy with a stop sign. He hasn't seen, say, a policeman with a flashlight or something. And so the person at the headquarters then has to say, oh yeah, okay, the car's going to go this way. And a minute later, that gets downloaded to the cell network, and the car drives on its way. And it's basically following the exact outline that this person, the person who's gotten AI out of trouble, has it's gotten coached. It gets the end of its model, and it doesn't know what to do. So this works really well, except when you're using AI in freeway speeds, and there have been a notable number of really awful accidents involving AI and self-driving cars, or cars that are advertised as having full driving functionality, whatever they call it. Anyway, so you can't stop a car in the freeway and have it phone home and get someone to work it out of a problem. It's got to make its best guess and just march on. So the two examples I want to use of this where there have been accidents are, a car gets to a left-hand exit on the freeway, and it probably sees the two lane markers moving away from each other and says, oh, if the lane's getting wider, I'm just going to drive down the middle. And it just runs, in this case, it ran straight into the concrete divider that then split the lanes. The left lane was going to go up over an overpass, awful accident. And the reason that the reason the AI failed on this is probably because it never got trained, right? The AIs work really well as long as they've seen what happens already. They've been trained on it. If they've never been trained on the experience, they have no clue what to do. And in this case, the AI had never seen this, and bam, straight in. The other highway speed AI problem that we've seen in the States is cars running on self-driving mode, running into the back of emergency vehicles. Fire trucks in the United States, when they're at an accident scene. I used to be a firefighter. I can close my eyes and see it. They have big red lights, and they flash one side the other, one side the other, so that it's really obvious as you come up on the accident scene that it's a fire truck. But if you don't train on a fire truck, you train on cars that are stopping. What do cars that stop look like? Oh yeah, they've got 2 red lights, right? So the AI sees, it doesn't see 2 red lights, it sees one and then the other, and one and then the other. And in the United States, a flashing light on one side is a turn signal. So it just sees it as the turn signal. Oh yeah, no, the turn signal. Oh yeah, someone doesn't know what they're doing. They're flicking their turn signal back and forth. No, it wasn't trained on an emergency vehicle. So what happens? Boom, straight into the back of the emergency vehicle. So these are the types of failures that AI generates, and it's all about not having seen the condition that it encounters. So that's sort of a limitation. So in closing, I would encourage you to start using AI, but do it sort of carefully. I had a really great summer intern for 2 summers. He was a wonderful kid. He was the guy who did all the investigation on SIMD instructions. He did the actual, assembly language code. He figured out, read the processor manuals, figured out the timing, everything. He then went to Rivian, and I talked to him a month ago, and he said, yeah, Rivian said that there are certain parts that we can't use AI to generate code, but on the production line he can. So he used AI to basically generate code from him and used it as a starting point. And our organization says we cannot use AI for generating code, but I realized at the moment, if I want to learn how to use multi-threading in Python, which I don't know. So what I would normally do is I'd go to Stack Overflow and I'd type in my query, and then I'd also Google it and find code snippets, and I'd sort of put it all together. And I thought, wait a minute, I could just go ask AI to generate a figure out a problem that I would solve with multi-threading, and then ask AI to come up with a code, and then I wouldn't use that code, but I use it the same way I use Stack Overflow, and I use it as sample code. Right? I'd see what was going. If I didn't understand something, I'd go look it up on python.org, and then I could assemble what I was going to do. But I'd have this huge. It's like cribbing from the guy next to you on the exam. You'd be looking over your shoulder. Oh yeah, that's how he solved it. Does that make sense? So I don't think it's valuable to lift things in toto from AI for coding or for scripting or for solving problems. But I think it's a really good starting point. Thank you.